Hello everyone and welcome to today's webinar. I'm your host Jeff Rawlings, and with me today is Dr. Uda Hangen, our European Applications Manager from the nanoindentation business unit here at Bruker. Today Uda will talk about dynamic testing at nanoscale, an option we have appropriately named nanoDMA. Uda will cover the theory and idea behind nanoDMA, and we'll cover some of our latest applications. As always, feel free to post any questions you have during the course of the presentation, and at the end we'll take a few minutes to answer some of those questions. But don't worry, if we don't get to your question today, we will respond by email later this week. Okay, without any further delay, let me turn things over to Dr. Uda Hangen.
Thank you for the introduction. The next 40 minutes I would like to talk about the dynamic nanoindentation characterization, nanoDMA 3. Here's the outline of my presentation. I would like to separate the talk by two materials classes: the materials with elastic plastic response and those with viscoelastic behavior. The nanoDMA technology is performed on an instrumented indentation platform. It falls in between AFM technologies on the lower end and DMA test equipment on the higher end if we think about the affected sample volume. Throughout the talk I will present related application examples from the two materials classes. It is very easy in an indentation experiment to identify whether the material response is elastic plastic or whether it is a viscoelastic material. The load function on the left-hand side is applied to two materials using a Berkovich indenter geometry. On the right-hand side we can observe the material's response to the partial unloading of the indenter. The two materials, an aluminium single crystal, and polycarbonate, are of similar hardness and can be easily compared for that reason. The materials show a fundamentally different response. The single crystalline aluminium deforms plastically and elastically during the loading segments. During the unloading of the indenter and the reloading to the force level already reached, we find a straight line and an exact overlap of the curves. The sample plastic deformation continues as we are loading the indenter beyond the force already reached before. The load displacement curve demonstrates that the loading curve has elastic and plastic deformation portions, while the unloading segment is purely elastic. The polycarbonate sample has a lower elastic modulus. Therefore, the slopes observed in the load displacement curve are smaller. The viscoelastic behavior of the sample is apparent in the unloading and the reloading part of the load displacement curve. The hysteresis observed is indicative of the time-dependent deformation processes, namely the creep, recovery, and relaxation processes going on as soon as the material has been deformed. The Oliver and Farr paper from 1992 is analyzing elastic plastic materials behavior. The analysis has to be applied with caution when testing viscoelastic material. A fast unloading segment should be applied to reduce the effects originating from the viscoelastic response of the sample. The 30-second unloading of the sample can be replaced by a 100 millisecond unloading with a high bandwidth indenter. The nanoDMA mode is being used differently on materials with elastic plastic response and viscoelastic response. We will talk about depth profiling of a thin hard coating and high temperature creep on a PM2000 alloy as an example for the elastic plastic response. The applications on the viscoelastic material will cover the viscoelastic response of a 3D printed sample, a comparison of nanoDMA 3 and macroDMA tests on cross-linked silicone, and we will look at the construction of a polycarbonate master curve. The ultra-small materials research performed with the nanoindenter is enabled by the combination of a transducer, a sensor with a small inertia of moved parts and low intrinsic dampening that is actuated by electrostatic forces, and a state-of-the-art controller, the Performec 2 controller, which has an analog to digital conversion rate of 1 MHz. It allows to control an experiment with 78 kHz feedback loop rate, and therefore this combination enables to do step loads or step displacements in a very accurate manner. The quasi-static indentation process requires to record the unloading curve of the indentation experiment. The fit to the unloading curve is performed to determine the slope, the stiffness of the contact between the indenter and the tested material. This stiffness value is needed to determine the contact depth and hence the contact area. In the nanoDMA experiment, the fit to the unloading curve is replaced by observing a small oscillation of the tip with high frequency at the maximum load. The force amplitude of a few micronewton typically, divided by the displacement amplitude of a few nanometer typically, results in the stiffness reading, without unloading the indenter. The ratio of the dynamic force superimposed on the quasi-static force of the indenter is typically very small. It allows to continuously measure the properties as a function of contact depth, frequency, and time. Bruker's nanoDMA 3 technology utilizes a lock-in amplifier to analyze the oscillations of the tip. The dynamic experiment is driven by an oscillating force of a defined force level in micronewtons and a defined frequency. The displacement signal therefore contains also an oscillating displacement. This displacement is analyzed by the lock-in amplifier, and its amplitude and phase signal is determined with high accuracy. The nanoDMA 3 technology is allowing to perform a CMX experiment, an experiment of a continuous measurement of values x with time. X could be the hardness or the modulus of the sample. During the dynamic test, it's not only the force and displacement that is recorded with time, but also the output of the lock-in amplifier, the amplitude and the phase of the oscillation versus time. This allows to determine the stiffness versus time, and the force, the displacement and the stiffness are necessary to determine the modulus of the sample and the hardness of the sample. Hence, we are resulting in a CMX depth profile of hardness and modulus of a sample. In the following, we want to employ the CMX depth profile to thin films applied to a high-strength steel substrates. These thin DLC films are mostly elastic plastic as well as the substrate. In the present slide, you can observe an image of the edge of the film on a substrate. Yellow is the film, the DLC coating, and blue the substrate. From this in situ SPM image, we can also determine the roughness of the sample and the step height of the film, which is the film thickness. nanoDMA 3 experiments for CMX depth profiles have been performed already on 3 coatings on a steel utilizing a Berkovich indenter. The steel substrate profile is plotted in blue. it shows almost no trend with the penetration depth. Only very close to the surface a slightly higher hardness is observed. The orange and red curves show the behavior, the depth profile of 3 different DLC coating thicknesses. Towards large penetration depths at 140 nanometer depths, we are observing almost the substrate properties of the sample. At a very small penetration depth, all 3 DLC coatings show the same hardness, around 20 GPa, but the transition from the film hardness to the substrate hardness is different and depends on the thickness of the films. The next application example utilizes nanoDMA 3 together with the Exol high temperature stage, which is used for nanomechanical characterization at temperatures of up to 800 degrees C. The Exol high temperature stage has a low thermal expansion design and a tight temperature control. It has a uniform sample temperature and the probe tip is heated in the uniform environment. We are using an atmosphere control, a shield gas of 95% nitrogen and 5% hydrogen. This shield gas is fed in between the bottom part of the stage and the covering heater of the stage and is protecting the sample and the diamond tip that is used for the indentation. A creep testing experiment of 10 minutes shall be employed at different temperatures on the PM2000 alloy up to 700 degrees C. The tip is heated up prior to the contact with the sample by the convection of the gas and by the close-by heaters in the Exol heating stage. We are talking about an isothermal contact situation. A maximum load of 5 millinewton is applied to the sample and a small dynamic load is superimposed to monitor the stiffness of the contact throughout the time of the experiment. This stiffness of the contact is used to determine the modulus of the sample in the first part of the experiment. In the second part of the experiment, the stiffness reading is then being used to determine the contact area and the penetration depth of the indenter. The nanoDMA 3 mode incorporates a reference frequency technique for thermal drift correction during the course of an experiment. On the right hand side is the stiffness versus the contact depth on fused quartz is shown as a room temperature experiment, and it shows that there is an identical relation between the contact depth and the stiffness of the system. Now, by monitoring the stiffness of the contact during the experiment, we are able to tell how deep we are in the sample. In the following, I want to discuss how a strain rate is determined in an indentation experiment. We are starting with the simple situation of a tensile test, where we have a known length and geometry of the sample, and the uniform stress and the uniform strain is observed during the tensile test experiment. The strain rate is the velocity of deformation divided by the length of the sample. In the indentation experiment, the situation is different because the indentation causes a stress field and a strain field under the indenter that is not uniform. The length scale that we have to determine a strain rate is the contact radius or the contact depth, and therefore the strain rate for the indentation experiment is defined as the speed of the indenter divided by the depth of indentation. The mean contact pressure under the indenter, which is the hardness reading, is the stress that we are applying. Using those two quantities, we are able to plot stress-strain behavior of the material. In a steady-state creep experiment, the strain rate relates to the stress to the stress exponent, and to the activation energy and temperature. On the right-hand side, a typical indentation test steady-state creep experiment is observed. We are observing the changing depths with time, where a changing depth will result in a changing hardness or stress under the indenter, and the velocity change that is observed results in the changing strain rate. This type of reference creep tests is performed on the PM2000 alloy. The PM2000 ODS alloy is an iron-based alloy with dispersed oxide nanoparticles of a size of around 20 nanometer. It is designed for high creep resistance. On the right-hand side, we see the different reference creep test curves, and we can observe that at temperatures of 23 and 300 degrees, no creep can be observed. At 500 degrees, a small creep displacement is observed and a more pronounced creeping behavior at 600 and 700 degrees C. The same data observed in a contact depth versus time plot are now converted in a log strain rate versus log hardness plot. Each of the curves is an experiment of 10 minutes. At 300 degrees, we are observing a very steep slope, a very high stress exponent M of close to 80. For the higher temperatures, the stress exponent is dropping. The material is more sensitive to the stress applied. Surprisingly, the transition from a high creep resistance to a lower creep resistance is already happening at around 400 to 500 degrees C, which is a surprise for an alloy that is designed for high creep resistance. Now we are changing to the viscoelastic matter. In the following, different aspects of a 3D printed polymer shall be observed. Different tests will be employed at room temperature or in combination with the exhaust stage at higher temperature to better understand the material's behavior. The 3D printed material is an polyactide. A constant strain rate is achieved by an exponential loading during the experiment. We are superimposing a dynamic frequency of 110 Hz, achieving a small displacement amplitude of 1 to 2 nanometers. Different strain rates are achieved by the load function shown on the right-hand side. The viscoelastic response of the material to the different strain rates shows that the reduced modulus is not depending on the strain rate being used during the test. But the hardness, the stress under the indenter, is changing with the different strain rates 0.01 and 0.1 per second. If we are changing the exponential profile of the load function and we switch between a fast strain rate of 0.1 per second to a slower strain rate of 0.01 per second during the experiment, we are able to observe that the stress under the indenter is responding to the different strain rate. We see for the green curve that we started with a strain rate of 0.1 per second, and at a contact depth of 400 nanometer, the strain rate has been changed to 0.01 per second until a depth of around 700 nanometer. Within that range, the hardness is coinciding with the hardness of the low strain rate, but before and after the lower strain rate segment, the hardness is coinciding with the hardness observed in the higher strain rate of 0.1 per second. The modulus is not affected by the experiment. Similar to the PM2000 alloy, we can plot these creep tests in the log strain rate versus log hardness plot, and the constant strain rate tests from 0.01 to 0.5 per second are plotted as dots on the top right, while we also performed a 1-hour creep rate experiment. All of these experiments fall on one line, which indicates that we have one creep process going on in the sample. Changing the temperature will change the material properties of a polymer dramatically. In the movie, we compare the behavior of a 3D printed polylactide at room temperature, well below the glass transition, and after heating it to 90 degrees C in hot water, above the glass transition temperature. The printed polymer behaves stiff and fully elastic at room temperature. But at 90 degrees C, the 3D printed polymer becomes very elastic and is easy to be deformed. When cooling down, the shape of the 3D printed polymer is permanently changed. The glass transition temperature is a characteristic property of the 3D printed polymer, where the structural changes result in a change of the strength. The 3D printed structure is not stable above glass transition temperature. In the following slides, the exhaust stage will be used to control the temperature of the sample. The exhaust stage allows to control the tip and the sample temperature very tightly, and it generates a small microenvironment of uniform temperature that heats both the sample and the tip to allow an isothermal contact. The uniformity of the temperature in the exhaust stage is visible in the finite element model on the right-hand side. Two ways of mechanical test shall be employed in the next slides to measure the viscoelastic nature of polylactide versus temperature. In the first experiment, the creep of the sample after a step load and recovery of the sample after a step unload is observed. A high bandwidth indenter system with small inertia of the moving parts is needed for the control steps in only 100 milliseconds. The creep is analyzed as the creep displacement divided by the time period of the creep segment, and its unit is nanometer per second. The recovery is measured in a similar way. The data points represent 3 measurements of creep and recovery each. The hardness value is determined from the fast unloading after the holding segment at maximum force. Both plots show signatures of the glass transition. The creep and recovery reaches its largest value at the glass transition temperature. The hardness drops by more than a magnitude from room temperature to 100 degrees C. An accurate control of temperature is necessary because the changes happen within 5 degrees. NanoDMA testing requires a proper modeling of the test equipment. The oscillating indenter has got a spring constant K, a mass of the indenter M, and a system dampening coefficient Ci. A dynamic calibration in air is performed to accurately determine these constants. During the indentation test, the sample contact stiffness Ks and the sample damping coefficient Cs will be determined. In the nanoDMA test, a small dynamic amplitude of 1 angstrom to 5 nanometer will be applied. The contact area is assumed to stay constant during the load cycle. No opening and closing at the edge of the contact area is observed. Elastic deformation occurs in phase with the applied oscillating force. Viscoelastic deformation causes a phase shift. This jumping rubber ball is an analogon to the quantities measured in a nanoDMA experiment. The ball is falling from one height and is losing height with each jump. The remaining height represents the stored energy. The lost height represents the lost energy. These values relate to the storage modulus and the loss modulus. The ratio of loss to storage modulus is the tangent delta value. While the interaction between the ball and the floor represents a large number of frequencies, a nanoDMA experiment is performed at one frequency at a time. 5 nanoDMA tests with a frequency of 10 Hz were performed for each temperature. The displacement amplitude is 1 nanometer. A typical load displacement curve with a 10 Hz dynamic test at the maximum load is visible on the right-hand side. This is the result of the nanoDMA test at different temperatures. A peak in tangent delta is indicating the glass transition. At the same time, a drop is observed for the storage modulus when going from room temperature to 100 degrees C. The tangent delta peak temperature matches with the peak temperature in creep rate observed before. Both approaches result in the same glass transition temperature. However, only nanoDMA3 is able to determine storage and loss modulus and tangent delta that is comparable with macroscopic DMA testing. This slide shows a comparison of nanoDMA to macroDMA storage modulus and tangent delta values for 4 silicon samples with varying amount of cross-linking agent. The samples are tested at room temperature with frequencies from 0.1 to 300 Hz. The triangles indicate the values determined by macro-DMA testing, while the circles indicate values determined by nano-DMA testing. The comparability between the two values is very good. However, there is still a small difference. This difference could as well originate from the uncertainties of nano-DMA testing or the uncertainty of macro-DMA testing, as pointed out by Donna Ebenstein in this publication. In a nano-DMA experiment, the frequency domain and the temperature domain is exchangeable to some extent. This is shown on a polycarbonate sample by measuring storage and modulus as a function of both frequency and temperature. The peak of tangent delta can be reached at different frequencies by changing the temperature. This plot is visible on the left-hand side. The tangent delta value at 10 Hz shows a lower temperature than for the tangent delta value at 300 Hz. On the right-hand side, the temperature is being kept constant during the experiment and the frequency is changed during the experiment. Here, the frequency value of the tangent delta peak shifts according to the different temperatures of measurement. By clever experiments, the viscoelastic properties can be predicted over a broad frequency range, even outside the experimental range of the actual measurements. The complete description of the polymer behavior is found in a so-called master curve approach that combines different frequency sweeps at different temperatures to one single plot. On the left-hand side, the master curve for the storage modulus is visible, while on the right-hand side, the master curve for tangent delta is visible. This plot summarizes the complex viscoelastic interaction of a polymer at different frequencies and temperatures. At the end of my presentation, I would like to conclude. nanoDMA enhances the possibilities of nanoindentation testing. It allows to determine depth profiles of hardness and modulus in the CMX mode. It allows to efficiently test materials creep in reference creep experiments at elevated temperatures up to 800 degrees. On viscoelastic materials, nanoDMA is a method of choice that determines tangents delta, storage and loss modulus, and in conjunction with the exhale stage, it allows to determine the glass transition temperature, comparable to macroscopic DMA testing. Thank you for your attention.
All right, thank you, Uda. That was a great presentation. So now let's take time to answer a few questions from the audience, and remember that if we don't get to your question today, we will respond to you individually by email. So the first question I have today is, how long can I run a creep test using the reference frequency technique? Could it be hours or even days?
The reference frequency technique can be used for several hours if you want. Since the maximum number of data points is limited that can be recorded per load cycle, the data rate will go down for long tests. We have been performing reference frequency tests up to 10 hours so far.
Okay, great. Next question. Can I use the CMX depth profile technique to measure film thickness?
It is difficult to determine the film thickness from a CMX experiment. Only in the case of a very soft material on a hard substrate, the transition of hardness and modulus will be very steep, and it could be possible to determine it approximately. But in most of the cases, we will see that the substrate effect causes a transition from the film, the thin film hardness and modulus values, to the substrate hardness and modulus values. This is because the hardness test always averages over the deformed volume under the indenter. I can pull up this additional slide that shows you the volume of the deformed volume under the indenter. So you see here for different penetration depths of 50 nanometer to 200 nanometer, the indication of the depth of the indenter, it's a gray triangle on the top, and the size of the deformed volume, which are the red circles under the surface. If you imagine to have a thin film, then the thin film tested will be only a portion of this large deformed volume, and therefore with the smooth transition that we have for hardness and modulus measures from the thin film properties to the substrate, it is not easy to determine the film thickness.
Okay, final question for the day. What is the maximum force I can use with nanoDMA? Can I use it with the high load head?
The maximum load used during a nanoDMA experiment depends on the transducer being used. The 10 millinewton standard nanoDMA transducer allows for a maximum load of around 9,500 micronewton quasi-static load and 500 micronewton dynamic load. But on the OmniProbe or the multi-range nanoprobe, the maximum load for a nanoDMA experiment can be going up to 10 Newton.
All right, thank you, Uda. Well, that's all the time we have today. Remember to check your inbox for an invitation to our next webinar coming up later this month. I want to thank Dr. Uda Hangen for his time today, and thank you all for joining us. We hope to see you next time. Goodbye.